Hello, and welcome to today's episode of Rawkode Live at the Rawkode Academy. Today, we're doing a hands-on session looking at how Rust and asynchronous programming work together. Before we do that, there's a little bit of housekeeping. Please like, comment, share, and subscribe, all the things on YouTube. You can always find this channel available at rawkode.live. Also, we have membership options available and courses where you can come and learn the complete guide to InfluxDB. So check out the different options available there, and feel free to jump into the Discord. We have around 500 people in there now talking all things cloud native, Kubernetes, and everything in between. So come and say hello, and I look forward to meeting you. Okay, so because I am not a Rust person, well, I'm trying to be, but my asynchronous Rust is pretty poor, as Senyo is going to find out. We have a wonderful guide today. So hey, Senyo, how are you doing?
Good, thanks for yourself.
Yeah, I'm doing all right today.
Awesome.
It's always fun to be able to write a little bit of Rust for people, so it's going to be awesome.
Yeah, I'm sure it's going to be good. I'm excited.
Awesome. Can you tell us a little bit about you and introduce yourself to the audience, please?
Yeah, sure. So yeah, I'm Senyo, as Dave's mentioned. Cool. So yeah, I work as a platform engineer at a company called Aerobotics. It's a company in Cape Town, South Africa, where I live. And yeah, we build software for the agriculture industry using a whole lot of nice buzzwords like drones, AI, machine learning, blah, blah. Really cool stuff. I actually started off as a data scientist, surprisingly. And then about like a year and a bit in, figured I enjoyed engineering more. And so moved over. And then, yeah, I've been like doing Rust like in my free time for like a year roughly. So yeah, it's pretty much how I ended up here.
I'm assuming, being originally a data scientist, you must be a Python developer as well, right?
Yeah, I know a lot of Python.
So what caught your attention about Rust?
So at the time, so this was last year. So yeah, last year I was basically learning a bunch of programming languages. So last year was like my first year as a full-time developer, and I was just learning languages because everyone's like learning new languages makes you a better programmer. So I started off with Haskell. That went terribly.
Wow, jumping in the deep end.
Yeah, I know. Wasn't a great time. Honestly, couldn't really figure out left from right there. And so then moved on to I tried Clojure. That was a great experience. Did a little bit of Go, and then at some point I was like, let me learn Rust. And I read the book. I know, yeah. I mean, just from there, it just caught my attention as like a really interesting language, and it also solved a lot of problems that like I had seen developers make in Python, myself included. So, for instance, like a function just returning none or some random value or whatever, and then it blows up in your face at runtime or whatever. So there was situations like that, and I was like, Rust has these nice guarantees, and it kind of like forces you to program it in a bit of a better way, in my opinion. So that kind of like just stuck with me, and then I've stumbled upon awesome Rust mentors, and then from there found a bunch of people in the Rust community, and then just stuck. Like that was that was it for me. So yeah, since then, pretty much been doing Rust like in my personal time as much as possible.
Yeah, I think the Rust community should be like an example of how to make a welcoming programming community. I'm just always taken aback by how happy and charitable everyone is with their time and their knowledge. Like, just it doesn't matter what your problem is or what you're running up against. There just seems to be always someone there willing to help.
100%. Yeah, it's really amazing, and I think it's probably one of the biggest contributors to our Rust is doing so well as a language. Just because it's a difficult language to learn, and so having a community that's there to support you through it actually makes a world of difference. So,
yeah, I've been writing Rust for a little while now and still bang my head against the table quite often. So it is definitely difficult to learn. But I am writing much more functionally correct code because of like the type system and the guarantees and all that. Yeah. So awesome.
Sure.
All right. Can you then do us a favor and maybe just tell us a little bit about what we mean by asynchronous programming?
Sure. So yeah, so just for context, like I started learning about like async, I think late last year. Well, I mean, I started learning about Rust late last year, but it's been an interesting journey. And so the I guess the most exciting thing about async for me was that I could actually learn like the details of it. And so kind of like how I got here. So with async programming, like the main idea is to solve, let's say, a class of problems that allow your code or applications to be more scalable. And so you basically want to run like concurrent software. So you want to handle multiple tasks all at one time. And this is good for things like web servers. So I guess that's like the canonical use case, where you have like multiple in-flight requests and you want to be able to handle them all. And obviously, if some are taking extremely long or your concurrency model isn't that great, you're gonna have like requests backlogged and then just start getting 500 and blah, blah, blah. So yeah, async programming kind of like came in to fit that void as far as I understand. And so the main use case or where it fits in the best is with IO bound tasks. So that's with most of the time taken for their like execution is, or it's dominated by waiting. So if you can think about it like making a database call, for instance, you do a bunch of work, make a database call, wait until it resolves, until you get your information back, and then you can continue working. So there's like a big span of time that's spent waiting. And so effectively what you want to do is kind of like maximize the amount of time that the CPU is being utilized. So you don't want to keep waiting. You don't want to have this dead time where a request comes in and then you've got to wait and then nothing happens between when you make that request to the database and when you get the information back. And so async programming kind of fits in that void by allowing tasks to basically like give up or like yield the execution to the CPU at points in time and say like, I've made a request, I'm going to be busy waiting, so something else can run in the meantime, and then when that thing finishes run, or like when I'm ready to run again, I'll let you know and then I'll proceed to run. And so that it's just kind of like unlocked a lot of performance. And so yeah, I mean, yeah, that's pretty much a long explanation.
No, that works really well. Like I think when I first started working like in code professionally, and I won't give you a year because that'll show my age, but I was working with Perl and PHP languages which didn't actually have like any native concurrency or asynchronous primitives, and yeah, blocking the request. Well, like a request comes in and then blocking until you make some other external request and then send it back.
Yeah.
It's just not going to ever scale, right? Like concurrency and asynchronous.
100%. Yeah, I've had like quite a bit of experience with Django's kind of like sync model. So it's kind of like basically you can think about like a thread per request. And so what happens if any part of your request is really slow, then all of a sudden you get this like huge backlog of requests coming back, because something might take like, I don't know, let's say like in a bad example, for instance, like if something took 2 seconds and your requests are coming in at like every millisecond or something, obviously things are going to go wrong, right? so yeah, async really fits that specific problem space, and yeah, basically solves for that.
Yeah, I think maybe a lot of the people that subscribe to the channel may be familiar with Go, which has a relatively hands-off asynchronous model in that you never really need to worry about it. You just say, go run this thing in the background.
Yeah.
Rust isn't quite like that, right? It's a bit more complicated.
Yeah. Yeah. I actually think like Go's way of doing it, like, okay, I don't have very informed opinions here, but I do think that it's actually quite a nice way of handling it, in the sense that because it effectively does the same thing, but just behind the scenes. So you as a dev don't have to worry about actually writing like async or wait. But I don't actually know which one's better, or like the ergonomics of either. But yeah, in Rust, I think Node, JS, Python, and a few others, yeah, it's really explicit. So you'd have to write like, pepper your code with async or wait and have your red or colored functions, as that essay says.
The Rust model seems to be really similar to the Node one. At least I see a lot of similarities, and even just the syntax and some of the, like, for me, the problem parts, it's always like you have to define your function as async, and then it has to be called from an asynchronous context. You can't just go throwing around awaits anywhere, which in the Go world is unheard of, because in Go you literally just put Go before a function name, and that's it, right? It just does it. But with Node and with Rust, the similarities are there, and I have to actually think up front about where I need the concurrency to happen or whatever. And I think my first time trying to write asynchronous Rust and realizing that I had to have this executor context and the main function that then delegated the access and blah blah blah. I was just like, it's difficult.
Yeah, it is definitely difficult. Maybe a little bit overwhelming. I guess for me, like that was my introduction to async programming in the first place, so I kind of missed it.
Well, you're going to make it easier for all of us today, right?
Hopefully. But yeah, I really enjoy, like, so far as much as played around with async Rust. Like, I've enjoyed it so far, but I have heard there are some pain points, I think, for a lot of people that are using it in production. So, but it's also still new, so we'll get there.
All right. Well, how do you want to kick this off? Do you want to? Will we move over to the screen share and start writing some code?
Yeah, let's do that. Let's definitely. I think that'll be fun.
All right. We can see VS Code, but you might have to bump the font size up a little bit.
Okay, cool. Yeah, let me do that.
I think you can just Command plus a few times, or change. That would work too.
Yeah. Let's see.
Go 24. That's what I use.
Okay, cool.
Yeah, now we're kicking. I like it.
Awesome.
I bet that's massive on your side, though, right?
Yeah, no, it really is. Really is big, and it's funny because I use like 10 or something ridiculous like that as my normal font. So 24 is huge, but it's actually a great quality of life.
You've got a hello from Javier in the chat.
Hey, it's not Javier. Yeah, I know him quite well. Cool. So yeah, I was thinking like it would be cool to kind of like run through just a bit of the kind of like basics of async, and just kind of like walk through some very beginner stuff and kind of like break some sort of like assumptions that we might have of it or whatever. So
perfect.
Cool. So firstly, one thing I think that's become like a big deal in async is like the executor. So, we've got like Tokyo and async standard, and then they're not entirely compatible and whatever. So you basically have to choose your one upfront, and like ecosystems are built around each one. For this use case, I'm going to use Tokyo purely because I know some stuff about Tokyo and don't know too much about async standard. So it's nothing against the async standard peeps. But yeah, I mean, it's just basically all I know. So basically just like a quick, just running through like a quick, creating a quick asynchronous function. So Tokyo's the executor, and then it's got like an entry point. So in this case, this async func main, and yeah, I mean, this is basically all we need to do to make code asynchronous. So we can actually then also increase the font of my let's see, terminal.
I think the size of the sidebar is okay if that's what you were worried about. Oh, the terminal.
Yeah, the terminal. Let's see.
Oh, there we go. Better? Yeah, perfect.
Cool. Sweet. Cool. Yeah. So this is basically all you need to do to make a asynchronous, or make your code asynchronous in the beginning. For the purpose of this one, I'd prefer to use, so you can use multi-threaded or single-threaded async executor. What's going on now? What did I do? Sorry. think that might work. Yeah, there we go. Current thread. So yeah, you can have a multi-threaded or single-threaded one. For the purposes of this bunch of work, I'm going to just use a current thread, which is just a single-thread executor. I think it's a bit easier to understand the model. So I actually have this image here that I was actually writing a blog post at some point that I never got to finishing. But you can imagine that, like, let's say we have task A and B here, and it's executing. So this portion is where it's doing some work. And this part where it's empty is it's waiting. Similar for task B here. Both of these tasks will run on like the same thread. So task A will run. It will just start with task A. Then when it gets to this yield point, it'll give up control. So in async, tasks are cooperatively scheduled, which just means that they themselves tell the executor when they're like blocked, and then they'll give up the CPU basically. And so it works on like, so you have to have like basically like good actors. So in this case, what will happen is if you had like a CPU bound task and it never yielded the CPU, then nothing else would be able to run it. It will all just be blocked in essence. But yeah, we have this like task A, which runs, and then it yields the CPU, and then task B will start running. But it's all on the same thread. This is a bit easier to understand than having it on multiple threads. It does the same thing, but like on multiple threads, effectively. Cool. So yeah, this is basically all we need to have an async function. And if we cargo run this, hopefully it will compile and work.
Yeah, I've heard the Rust compiler is really fast. Said nobody ever.
Literally. Also on a MacBook, it's arguably also not as fast as on others. Cool. So yeah, we run this function. We've got a hello world out. Feels very synchronous, so nothing too crazy. And effectively, it's not, but effectively it's run in a synchronous fashion. And just to kind of like unpack this, so this Tokyo main flavor current thread is effectively the same as this. So it's obviously a macro, and it does the same thing as, let's see, I can comment this out. So these two things are equivalent, barring that there's no comma here. And so basically what happens is it creates a new runtime, and then it has this block on method. And what this does is, as it says here, it'll run the feature and then block until it's complete. And so basically this here is your feature, and you have this root feature. So features are often made up of other features. And so in the case of, like, let's say a web server or whatever, you'll have like this outermost feature and then all of your tasks running. Oh, yeah, run this slide here. All of your tasks running within that feature. And then only when this root feature, so the like top level feature resolves, will this finish. And so, yeah, basically we have this async function here, which does the same thing. So this should effectively give us the same output. Let's see. Yeah, hello world. So we've come full circle and pretty much got the same thing. But yeah, now we can try and do some more sort of like useful stuff. For instance, so let's say we wanted to so let's say we wanted to just make like a request using request. So we can use a request is async. Basically, it uses Tokyo underneath. And so let's say we can create a client.
So request is a HTTP client?
Yeah, it's a HTTP client. So you can get a new client. I think will work. Let's say get. What is this URL that I'm thinking of? Rustlang. Okay, cool. So this .send is a this actually returns a feature. This .send, and then we've got to await that feature to basically run it. So one thing about Rust's async model is that features don't run until they're polled, which is basically just to say that they do nothing. They're lazy by nature, so they do nothing until you kind of like force them to run or drive them to run, which is what this await does. So if you don't use .await, nothing will happen.
So if you create a future and never query the result, then that future will never run.
So yeah, if you never await a future, it'll basically never run.
Okay.
So we can actually like test that out. So firstly, let's maybe just like print a let's just do something simple. So in this case, the same thing. So we'd expect this to return like a 200. It'll just be like this one, 200. I should definitely get a fast computer.
It's not you, it's the compiler.
Cool. So we got this 200 out. But let's say we didn't run this. So instead, we just had send here and then did nothing with that. With this. So now you can actually see from Rust Analyzer that this output is a future with some response in error.
Yep.
And okay, now we're getting an error here. So this, nothing will happen here, basically. Like there's nothing that's going to get. You can't actually print a feature.
Can I make a suggestion? Could we like create a function that just touches an empty file on a disk and then schedule that and then not await it, and the file wouldn't be created, but if we did await it, the file would be created?
We can do that. We can do that. Let me figure out how to do that.
Or I guess even just even a print line statement would work. Like if we wouldn't see the print hello if the future or the asynchronous function was to print hello, we shouldn't see any output. I guess it would be the same effect.
Sorry, what are you saying? I missed that.
Yeah, I was just saying your idea is better. Like if we just do a print inside of the future, like if we create a new function called async print hello, like it should never print hello if we don't await it.
Yeah.
Rather than trying to remember how to do the file system calls, because I definitely don't remember.
Yeah. So let's say print hello. So it takes nothing, and then this just goes Rawkode. Cool. So in this case, we could actually just say, so you can say like let feature equal. So in this case, like we would expect, so pretty much this hello Rawkode wouldn't run, but this print line would.
Yeah.
So if we do that, then that's pretty much what should happen. Okay, so now it's telling us that we didn't use.
It's just a warning. I collect warnings.
So you can see like, this hello gets printed, but then if we go like future.await, then we should see hello Rawkode and then the hello, right? Yeah, so that's pretty much what we've gotten by awaiting this feature. An interesting thing, though, is that this technically is still just running synchronously. So even though we've got this like async and Tokyo is running it, blah, 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 there's not multiple tasks being run at the same time. So we can do that just using, let's say, we can make some multiple requests. And so like some interesting things here might come up. So if we have and then make that same request again. So client got it. Just give me a sec. So yeah, there's quite a few interesting things that could happen here. Cool. So if you've got this and we kind of like duplicate this again. So if we have
so you're going to make two HTTP requests.
Requests,
okay.
Yeah. So if we do that, then okay, let's call this like results or response 1, and then this response 2. What will happen is that still in this setup, okay, let's do like number 1.
This will still be synchronous?
Yeah, it'll still basically be synchronous. So we'll have and then
it's live typing.
Yeah. Cool. So in this case, it's basically actually still synchronous here, because tasks aren't really being spawned to run asynchronously. So in this case, it'll still run. So even though this result 1 will be like an IO task, so it has to wait for a response, it'll just still run in the order that it's there. And so we can actually get around this, right? So still in order, and if you run it multiple times, it'll continue to be in order. And so to get it to actually start using async properly, I guess, then we can start spawning tasks. So Tokyo has this thing called spawn, which I think I need to use Tokyo. Yeah. And this spawn takes like an async function, basically. I copied it right now. Cool. Right. So yeah, and so this will spawn another task onto the executor, and these will run in asynchronously, basically. But we might also find some weird behavior coming out of here, which could be quite interesting. So let's say, so we have that. Then what we want here, time. Cool. So, what did I do now? Doesn't matter. Cool. So now we have these 2 tasks basically being spun up. So this spawn will spawn an asynchronous task onto Tokyo, and this will do. So these won't block. So what we'd expect here is because these get scheduled asynchronously, you would expect this to run this print line ran async first, and then whichever order these complete. It might still complete in the same order it's been written, purely because the one request happened earlier than the other, but sometimes it doesn't. I had fun yesterday figuring that out. So if you run that, then cool. So yeah, so this is actually an interesting outcome here, and so this has to actually do with the fact that like there's when I was talking about having root futures and futures, or a root task and then tasks being spawned within sort of like this root task, or being a combination of other futures. What technically happened here is that block on function that I had earlier, or that I showed earlier, it only waits for the top level future to resolve. And so what's happened is that these 2 tasks have spun off, but then the top level feature is basically like this in essence.
Yeah.
And so when it got here, then it's finished. The top level feature is finished. And so it just doesn't complete the rest. So a quick way of actually handling this is to use Tokyo join. And this basically just says it waits for each task to finish before completing, basically. So it'll wait for all of these. And spawn returns like these things called join handles.
Yeah, I think I've had this problem before when I've been doing asynchronous stuff. Like, why is it not running?
Yeah, it's a bit of an interesting one. So yeah, in this case, now we've got this like Tokyo join, and then this will basically wait for these two to finish. So I don't know which order they'll finish in. It can change. It could be in the same order. But now we'd expect to see run async and then the status of these two things being printed. Cool. There you go.
Oh, two first.
Oh, two first. Cool. So now you can see that now this is actually all running asynchronously, which is the goal and exactly what we wanted out of that system, basically.
Okay, can I just summarize this so that I make sure I understand this all correctly?
100%.
Okay, so can you scroll up one line? There we go. Okay, so we have this Rust macro, which is the Tokyo main, and where you're setting it to use an executor, which is current or a single-threaded. That macro is doing the boilerplate that you pasted earlier, which sets up a Tokyo executor, blocks on an asynchronous function, which is in essence just our main function.
Yeah.
Now here you have two different requests using two different clients to the Rustlang website, which are being blocked on using the await syntax. Those are both spawned asynchronously using Tokyo's spawn construct, which just takes a asynchronous function and runs it in the background and returns you a handle to that asynchronous task. And then at the bottom, you are using a Tokyo macro again, which allows us to just wait on all of those pending tasks that we have by passing in the handle and letting it do its thing.
Yeah, pretty much.
Okay. I got one question then. Like, is the standard procedure to then... let me say this right. Do we need the two clients, or could we create the client on a higher level in a function and pass it into the asynchronous functions? Or would you just try and isolate that as much as possible and have multiple clients?
So it's a bit of a difficult one, mainly because it's not like extremely concrete in my mind yet. But in this case, when you spawn something, like the task normally takes ownership of those variables in that case. So in this case, client, we want it to be owned by a certain task and all these tasks, and I'm not entirely sure why. Though I mean, like just a broad assumption there is you want a task to own like its entire or like all of the variables it uses, because tasks can also get like shipped across threads, for instance. So it might, let's say in a multi-threaded context, it might start off on thread 1, but then end up on like thread 3, for instance. And so I'm like pretty sure that's probably a big reason why it needs to own its variables. And so I'm not sure about kind of like passing in the same client into multiple tasks. I'm pretty sure it could probably be possible, but I don't have enough knowledge there.
Yeah, I'll take that. Also, I'm curious about the join handle. Is that a feature itself? Can we await the join handle if we wanted to?
I actually don't think so. I'm not sure. I'm not sure. I don't think it's. It's actually. Nah, it doesn't look like it.
Okay.
Doesn't look like it.
All right. We have a question in the chat as well from Russell, who's asking, is the lazy execution mechanism the same depending on the executor behavior? For example, if you choose multi-threads rather than a single thread, does an async function only get called when awaited as well?
Yeah. So that kind of like model with futures or tasks only being run when they're awaited, that's just like a Rust construct. How that's handled sort of like by your executors is just like an implementation detail. So yeah, it's basically just like how the language is solved for that. And I think the reason why it's built like that is because or for them to be zero cost. And so what's happened, at least from what I've read, is early on Rust actually had its own like sort of like green threading library. And so, but that had like global costs. So basically, it would put a performance cost on in using Rust, whether you use that set of functionality or not. And so, with having lazy features, it basically means that like no work actually happens before, and they're compiled down to state machines. And so no work happens before, so you can use them, and or you can like create them and use them freely. And if you don't await them or have an executor, then you pay no performance benefits. Obviously, then they're useless. But that's the that's the premise. So I think it's got to do more with the kind of like design constraints that Rustlang imposes by having that zero cost guarantee. And so that's why it's set up in this way, so that nothing like happens automatically. Whereas like in Python or whatever, once you start the event loop, it just does its thing, And same with like Node and others.
All right, perfect.
Cool. Sweet. And so so that's pretty much on some Tokyo stuff. I was also thinking it would be cool to kind of like run through a bunch of stuff around futures themselves, just because I pretty much find that interesting, and just talking around like how they're created, what they do, all of that jazz.
Yeah.
So let's do that. So okay. Sweet. So just give me a sec. Sorry. Cool. Yeah. So obviously we've been talking a lot about features and tasks and whatever. And so, basically like a feature represents, or it's kind of like canonical definition is it represents some work that will be completed in the future. So it's like some computation that will be completed in the future. Rust is a little bit different purely because that feature, like it has to be polled kind of like manually. And so you can see that, let's say, and so then we have these like async keywords. And so basically async is just a way to denote the function is async, but it basically just returns a feature. So if I do like this, like this feature is some async and just some number, you can see that this return is something that implements feature, and its output is an integer. If you make it something else like unit type, you get this like unit type output. Let me just use this one. And if you do like a string, you'll get an string. So a feature in Rust is basically something that, what am I saying? That is stuff. Is basically something that implements the feature trait. And so in this case, in this simple case, like we've got this feature that basically just returns 16 here.
Yep. Can people that are familiar with the Node ecosystem just replace future with promise in their head and it's like the same thing?
I think so.
It kind of looks that way, so I think I'll just try and do that.
I think so. I'm not entirely sure. I don't have too mumuch operating experience with JS or Node.js.
Lucky you.
Yeah, I avoided that one. Cool. Yeah. So I mean, we have this feature again, like we can go and do some work here, and this obviously won't do anything until we await it. Oh, sorry. Cool. So yeah, and so we have this feature, and so like a big question I had like initially when I started is like, what exactly is going on with the feature, and like how does it run? So we can actually do some cool stuff here. So I just need to just import a bunch of stuff. So let me actually just copy and paste this because it's just be way easier. Cool. So let's say we wanted to so we can make our own feature. It's actually not that difficult to make a very boring feature. So we're going to just do that. So let's say we have this pending feature.
Are you going to tell me that features are just a trait implementation?
Technically, yeah.
Everything in Rust is always a trait implementation.
Traits are beautiful. They're really great. So it's no wonder. Cool. So we can create a trait. What did I do? So yeah, we can create a trait by implementing feature for this thing that we've called pending feature. Cool. And this is basically the structure of that of the feature trait. So we have to have this type output. This is like an associated type. So we're just going to return basically nothing.
Oh. So it's just an implementation of a pull function that checks to see if the work is completed and then returns it.
Yeah, pretty much.
Nice.
And so, okay, cool. So what will happen is that when you poll, it will return this kind of like poll object here. And this can either be poll pending or poll ready. Those are the two like variants. So pending or ready. And so we're going to do something like really interesting here where we're just going to return poll pending and like print polls. So yeah, and so what will happen is like basically when the executor runs and you await a task, it'll basically start polling your task for you. And then there's like a whole lot of details there. So we can make a pending feature here. Cool. Cool. That's about a red. And wait that. So the interesting thing here is that basically, we'll see when it runs, whenever that is. Cool. So we've got this like I've been polled, and then now our executor is actually hung. So like there's nothing's happening. And the reason why is because, as I said earlier, like we've got this like outermost feature, and that feature, what's the word I'm looking for? Like, it's blocked on that outermost feature, and so this this one that we've created internally, it never completes. So by having this poll pending, it basically never completes, and so the outermost feature won't also complete, and therefore it just hangs, and so nothing happens. So we can also.
I'm kind of curious, it only pulled once. Like I would expect it maybe to pull more than once. Is that something that's then controlled by the implementation?
Yeah, so that's actually an interesting thing, and also like a great, or just like a thing that Rust did. So we can actually fix that. So let's say saw this trick the other day. It's actually really cool. So then I can explain it later. Okay, cool. So if you do this, I think this should work. So in this case, we should see a lot of output here. Hopefully. Yeah, you can
there
see
we go.
Great. Yeah, right? Stop. Okay, cool.
That's kind of what I actually expected that behavior by default. So maybe you can walk me through that one.
Yeah, cool. So that's basically like the way kind of like Rust is set up the system. So the idea is that when a task gets polled and it doesn't complete, you don't want to like keep polling it all the time. So you don't want it to be like this busy loop where it's like, hey, have you finished? Hey, have you finished?
Yeah.
Hey, have you finished? And then it keeps saying like, nah, I haven't finished, right? So what it does is that it'll set up. So we have these things called wakers, and wakers are basically a way to tell the executor that like, hey, the thing that I've been waiting for is now complete. I'm ready to be scheduled. So let me run effectively. And so what will happen is that your task will run, and then it will like yield. It'll say, it's pending. Then when it's ready to run again, it will call this like waker object, or it'll get this wake object and call wake, and that will reschedule you back onto the executor. So in this case with Tokyo, for instance, because we didn't reschedule it, nothing happens. Basically, it just like we've polled it once, and then it never tells Tokyo again that like I'm ready to be polled again, and so nothing happens until that happens. Like until you wake your task, basically, or your future.
Okay, got it. Thanks.
Does that make sense?
It does.
Cool. So yeah, so that's basically that. And where was I? Yeah, cool. So okay, cool. So now we can also have like this. We can just return ready as well, and so this will do what you would expect it to. Like it'll print out this I've been polled and then print hello. So cool. Yeah. So now we've got this feature that basically does exactly what we wanted to, and it's actually not that complicated as we've seen here. Like we've been able to create one, without too much ceremony. Obviously, real features are way more complicated. And so that's pretty much like that on having or creating your own features, and then wakers. Cool. I don't know if you have any more questions.
Yeah, I guess so. Like, people wouldn't really be expected to implement features on their own. In fact, it'd probably be discouraged, right? Just use just use what is already provided.
Yeah, pretty much.
Okay.
Yeah, and like there probably are cases where like it makes sense to create your own, but like most likely you just use what's in the ecosystem already or provided by like the library itself.
It's nice to see how it works all the way down. Like, now hopefully people have the knowledge that they can add the Tokyo executor to their applications. They know that they can then go and create features or use functions that return features, and how to block and await on these things or let them run asynchronously.
Yeah.
And just seeing that it's just a trait implementation with a pull function on it was quite nice. Like, just being able, I mean, I should have thought about it, and then of course it's Rust. Of course it's going to be a trait, but
yes, no, for sure.
Seeing it implemented is really cool. I like that a lot.
So yeah, it really is cool. I mean, like I think they've done quite a good job of the implementation details and like how it works. So it's also pretty exciting to do it yourself, even if it's something like very small like this. Only because it can seem like crazy. It's like nice to see or to know that it's not the craziest amount of magic. Like you can do something very simple and like put it up your own thing. Which is pretty cool. Cool. So like to kind of like end off, well, it's not end off because it's gonna still take some time, but thought it would be cool to like run through. So Tokyo has its own or it has like a tutorial on like making your own executor, and so I thought it would be cool to just kind of like walk through that. Just because it again like gives a bit more context into like how things are put together. I also found it like super interesting. Cool. So we'll make a new file here. Cool. So I'm going to be jumping back and forth, just like copying code from that tutorial.
Yeah,
so that's on like it's on their website. Like if you go to tokyo.rs and you go to like I think they've got something learn. They have a tab called learn, and you go to async in depth. They have a tutorial there. So yeah, I mean it's really, I encourage everyone, if you're like interested in the topic, to read through it, because it's really interesting. And okay, I mean, it's obviously a very simple executor, but it's not like nearly as complicated as you would have thought it would be, surprisingly. But
Yeah, it's
also,
simple examples that teach us, right? I mean, reading a
yeah,
complex example, I'm going to walk away more confused than I came along. So yeah, simple works well for me. I like simple.
Yeah, no, same, yeah, same, yeah. Cool. Just give me a sec.
Yeah, take your time.
Cool. Okay, cool. Sweet. Cool. So yeah, off the bat, we'll have this like. So we're gonna start off. I'll kind of go through it like. You start off with this like executor, and then we'll kind of like build all the constructs going down, um, which will be fun. Let me just see if I have everything I need here. Cool. So yeah, just off the cuff, we'll have this executor, and that. So yeah, first thing it'll have is like, okay, a task queue, and then let's say, trying to think of a descriptive name for this. Send to executor queue. Right? So we're just going to use crossbeam. So crossbeam is like, actually, I don't have a good description of crossbeam myself. I was actually just going. Let's see if it gives us. No, it won't give us anything. Nah, wait.
Yeah, that gets me every time with Rust Analyzer.
Yeah,
That if you don't use the code, it doesn't get all complete or anything like
yeah, that happens to me all the time. Right. So we've got tools for concurrent programming. That's what crossbeam is.
that. Okay, perfect. I know exactly what that is now.
It was better than any description I could give you, so we're just gonna go with that. Cool. So yeah, we've got this crossbeam channel, and so this will just be a. So there's going to be some details here that I might just like skip over, honestly, but it's cool. So and then we've got this like send.
So it's starting to look a bit more like Go now.
Yeah, yeah. In channels. So yeah, so we have this. What am I doing? Cool. So yeah, so for this executor, basically we have. So this task will kind of like create a thing next, but basically the idea here is that you have an executor, and in our case we have this task queue. So this is the like queue of tasks that the executor has to run. So when tasks get scheduled on, obviously backlog the queue, and then it'll just go through here to figure out like what to run next. And then this send to executor queue, I'm just calling it this just because it's easier to understand like exactly what it does. But basically, this is the sending side of the channel. And so what we want is for a task to be able to like send itself onto the task queue. And so we're going to just like pass this down into the task itself, in essence. And so that's kind of like why it's there. So just adding like some methods here. So we're going to add this in. Cool. So just creating a new executor. Cool. So So send to executor key. And task key. So this just creates a unbounded channel. So there's no like capacity, no like set capacity for it basically. And then we're just gonna return that. So task key. Cool. Then we have this function called run. Which basically it's going to be our entry point. So we're going to go like executor.run, and it should basically run all the tasks that are there. So this looks like task queue, and then we're going to pull the task itself. So here, all we're going to do is just like run through each task once it's received in the queue, and then just pull that task until it resolves, basically. And then the ask function spawn. Speed up some stuff here. So this, I actually need to figure out exactly why. Actually, cool. So this is just in the tutorial, so I'm just kind of like copying it from there. I'm just typing it out just so everyone can play along or follow along. But yeah, it's got like so this is the kind of like the trait bounds. The trait bounds. It's got to be sent, I think, because of crossbeam channel needs to be sent, and then this static, I'm not entirely sure. I'm not gonna lie. That's something I haven't wrapped my head around entirely. But I have a very strong feeling that it's got to do with. Actually, it probably doesn't have to do with pinning. It might. But yeah, that's something I'm yet to figure out entirely. And so
yeah, I just
cool.
throw lifelines around whenever things don't compile and hope for the best. I'm just like, yeah, sure, static, go for it. Does it work?
Yeah.
Done.
Literally. Oh no, this is the wrong send to. Oh.
So it seems here like what an executor is send and receive channel with a couple of functions to add stuff to the queue and then to run the queue.
Yeah.
Like,
yeah.
When you break it down like this, you're kind of like, this makes sense. Like,
That's really cool. It's really cool. Obviously, this is very watered down, but nonetheless, it's basically like the premise of what's going on. So now we have our executor, with the queue, and then you can see here in the spawn function, we basically pass this like send to execute. So a task firstly like wraps a feature and adds a little bit of functionality to it, like state management, I guess. And then we're passing this like send to executor queue. What's the number for? It's like sender, I guess. And the task will be able to use to basically like reschedule itself onto the queue. So cool. So that's that. We can then go on to like implementing our task. So I'm also just gonna copy this in. So cool. All right. Let me actually just make a new. So
Will that use statement work without a mod statement?
sorry.
You said use create task, but without a mod. Does that work?
Yeah, it does work. As far as I know. I think it should work. Well, we'll see.
We'll see here.
Yeah. If it doesn't, then we can just use mod. Cool. So yeah, we have this task. A task is just going to be a feature, and then that like send to executor queue, basically, which will be the same as before. So we've got this sender, and that takes in a task, and then this feature is it's just complicated, but basically, so it's basically
Dear, a pin and a box. Damn it.
yeah.
I'm out. I don't know.
And the mutex.
And a mutex, yeah.
And the mutex, yeah. It's
The only thing it's missing is arc, and then it's got pretty much all the words I hate.
So the mutex is to make it sync, because crossbeam channel requires things to be send and sync. And I think sync is a marker trait. Sync and send are marker traits. So that means that if all of it's like I forgot what the right word is, like variables or whatever that belong to task. If they are all sync, then task will be sync. If they're all send, then task will be send. And like if one of them isn't sync, then the whole thing's not sync, basically. So it's like it's an auto trait, basically. So this mutex is needed to make it sync. And then on pinning is something I'm still also just learning. But in effect, it's because Rust features Rust features they need to be self-referential. They need to have the capability of being self-referential, so they can refer to their own like variables that they constitute of. And so if they've moved, then you can imagine, like, let's say you have something sitting at like location X, and the feature then is moved in memory and it's pointing to itself, then that part where it's pointing to itself gets invalidated because it's moved in memory. So you want to pin them so that they don't get moved, basically.
So pin removes the move semantics then, like keeps it in the same bit of memory.
Yeah. Okay. So it basically disallows certain operations from happening on something that's pinned, basically. So yeah, so it doesn't actually like stop anything from technically happening. It just disallows certain functions from you using certain functions on those objects, basically.
There you go. That's the most important thing I think I've learned today. So now we know that we've got this dynamic trait thing of dynamic size thing in memory. So we wrap it in a box. We use a pin to keep it in the same point of memory so that it can refer to itself with a mutex so that we can control what speaks to it in order.
Yeah.
Got it.
Pretty much. That's pretty much it. Cool. So yeah, so then we have this task, and then we're just gonna implement some of its stuff. So okay, first, actually, what could be more interesting is to have this. Did I import this? I don't know. Okay, no, I haven't. Okay. I don't know if I've got this. I think I need to add it. Let's see. Sweet. So we have this thing called Rawkode, which basically allows us to implement that wake and wake by ref functionality. So that's also a trait. No surprise. And that's needed for for us being able to like wake a task and basically reschedule it back onto the executor. So in our case, we're just going to implement this wake by ref one.
Can I ask an adjacent question just now?
Yeah, sure.
What's the difference between standard future and the creates futures? I don't.
Oh, cool. So well, at least again from what I know, so when they stabilized like the future trait and everything, that's obviously what's in the standard library, and a lot of the like design and I guess API development and all that happened externally, similar to let's say like how Tokyo and Async standard are kind of like core functionalities of how you'd use async Rust, but they're not provided by the standard library. And so that was initially all in this like futures crate. But then some of it got stabilized and put into standard. But then there's still a bunch of functionality that's only available in like the actual futures crate. And so you'd basically use that to add like the additional functionality in essence.
Yeah, I got it.
Pretty much. So we have this schedule here. And so basically what's going to happen, or the premise here, is that when we call this wake by ref or wake, we're basically just going to schedule it back onto the executor here using this function, which we'll implement now. So let's schedule. Cool. So here, cool. So we've got this function schedule. Oh, and so a weird thing, like also like a gory implementation sort of like detail, but setting up these like wake functions requires kind of like some low level unsafe code. And so an easy way to kind of like avoid that is to use this arc wake. I don't understand like how it negates or how it solves that problem for you in effect. But yeah, it's basically kind of like a shortcut from having to deal with writing that like unsafe code yourself, basically.
Okay.
So then we're just gonna also then when you want to schedule a task, we basically call the schedule, which will get called by like these wakers. And this is basically sending it, or what I call this executor, send to executor key.
Yeah, I was going to say, where's executor coming from? You just threw me for.
Just threw away a bunch of words. And so yeah, we've got the send to executor queue, and then we send ourselves basically or this task to that queue. And then I'm actually just gonna copy and paste this side. So then, and then we also have this poll functionality here, which yeah, and so effectively when we poll this task, also because I've got 20 minutes, that's not too bad. So when we poll this task, we basically create a waker and a context, and that context is used when you poll the future internally. So we have a future attached to the task. This will never fail purely because no other thread is actually trying to unlock it. So you can just unwrap here. And then we pass that context into the future itself, which will then get called by that like future when it wants to wake itself up, basically, as well. And then the last part also, I'm just going to also copy and paste this in. Which is that spawning functionality. So this is actually quite simple. Where when we want to spawn a task, we basically create a new. So when you want to spawn a task, we basically create a new, a new task object, and then we send it to. This is not sender. It is. And then we send this to the task queue, basically. So that's what gets passed in here. This send to executor queue. So every time we spawn a task will just basically send itself or send a task to the executor to get to run, basically. So that's basically that. And those are the two kind of like big components. And then all that's left to do is create our own. What is this one? I have no idea. I will figure that out just now. So yeah, all that's left to do is like create our own feature. I also, for the sake of time, also just copy and paste that and just kind of like talk through it, which would just be like a lot faster.
Yeah, go for it.
Cool. But I also need to solve this issue now. This is, you're probably right, yeah. Let's see.
I think you still need to use, but you need the mod test first.
Yeah. I don't see what's going on here. What's going on? Unresolved module. That is super weird. Okay, we'll get back to that. That's probably why. Okay, let's see. So, I've got a lot of errors coming. Let's see, unresolved import. No, that should be fine. Cool, just give me a sec.
So what's the error on your use future statement?
It just says unresolved imports. I think it's just not picking up that it's there. Let me see if I can just like reload my window and see if that solves any of my issue, which I doubt it will, but let's see.
Yeah, Rust Analyzer does seem to flake out after a while, and I usually restart VS Code. So.
Yeah, it does happen every now and again, sometimes, but we'll see.
I think it's still building.
Yeah, it's still building a bit. Well, okay. So, no, it's still giving me errors. No, it's changed now. Cool. So that's fine.
Happier. Yeah.
That's definitely happier. Let's see if this works now. There you go.
Ta-da! There we go.
Back in business. Cool. Sweet. So, right, and then, okay, we can actually kind of get rid of all of this. Cool. And then there's just this last piece where we have a let me just get that solved. Cool. So we have this like future delay, which is it's almost like a sleep in effect. And so basically what happens is, I probably should have written this one out. But basically, what's happening is we basically want to delay for a certain amount of time. So we have this thing called an instant. Instant just gives us like an instant in time right now. It's basically used for comparisons. And so we want to say, we want our delay to be, what's the word, like from now plus 2 seconds, and then only after 2 seconds will we be finished. So in this case, what we have here is if the current time or like this current instant is larger than when we specified it to be, so like maybe like instant plus 2 seconds from wherever we are, then return poll ready. Otherwise, we then go ahead and set it up to basically tell us when to reschedule itself. So here, what happens is, okay, we've gotten the waker from the context, and then we're kind of using like a semi-hackish way, I guess. I don't know. But we basically spawn a new thread, and then we sleep that thread for that period of time that's left. So, if we wanted 2 seconds ahead and we're actually 1 second ahead, then we want to sleep for 1 second. And then once that's done, then we call this waker.wake. And this is important because if you don't call waker.wake at some point, then your executor will basically hang, or this task will never get finished or run to completion, purely because it never gets work and it never gets like rescheduled onto the executor to run. And then we have this like poll pending in this case. So this will return poll pending, and then once this waker.wake runs, it'll get executed, or it'll get rescheduled and then executed. So that's basically, you can ignore those. This waker.wake is basically what gets called here, the self.schedule, which then again sends it to the executor queue. And then I think we're pretty much good to go. So we can go. Let's actually do this. And then maybe okay, cool. So cool. So we get a new executor. Then we got to create a new future. So this delay. Then we want like an instant. I think we can do this plus. I think that should be fine. Cool. And then we want to spawn that task basically. So we want to spawn this future, and then we want to run basically. And I think that should do the trick.
So this should, and when you do a cargo run, create your new executor, create a future that we just created with the delay, which just looks for the timestamp upset. You then spawn the future, and then hopefully wait. And what we should see is, I was gonna say, let's get some print statements.
Let's say pending, cool, and then we'll say we are done.
Don't forget the emoji. I think we need like a confetti emoji or something.
Let me go grab one quickly. Okay, cool. And then this here, we can actually, this will be cool because then we can say like, we can see that the task, making the task back up. I don't know what the, okay, let me go get this great emoji from someone. Emojipedia. That's always a good one.
There's a shortcut on the Mac for emojis, and I can't remember.
Oh, really?
Yeah, I can't remember what it is because I've got mine set up as the function key. But I think that's
cool,
an option. But I think you can do like command shift and something. I'm going to look it up. Completely irrelevant now, but I'm going to look it up.
Okay, cool. Yeah, so we should expect it to pend, then to complete, like say, waking the task. Then we are ready. Hopefully, let's see how it goes.
Give you a drum roll.
Where in the run? What happened to my which? I don't know where I am in my computer. Okay, I think we're at the right place now.
It's Control, Command, and Spacebar for future reference. There we go.
Cool. Oh, now just to wait.
I know.
The fastest compiler ever.
I do like that they do make
It's
speed
not bad.
improvements. I do. It's easy to make fun of the Rust compiler, and I do it often. But I also appreciate that it's a complex piece of software, and people are continually trying to make it better. So,
100%. I mean, there's that also. It gives you a lot of guarantees. Like, it's basically a kind of like trade-off between what it offers you versus like how fast
yeah, definitely.
it compiles. So, yeah, it's all right. Let's see what happens. Okay. Pending manual task already. Cool. But then
It's still hung.
I don't know. It's still hung. But I have no idea why. Oh no, that makes sense because this is a blocking. This thing is still running.
Right. Okay.
And this blocks. So it worked basically.
So I guess if we added I mean, we don't need to do it, but if we checked and the tash cube is empty, we could just exit, right? Something like that.
Yeah, we could do that. But in theory, like, let's say if you're running a web server, you wouldn't want to do that, for instance, because you can get traffic at any point in time.
Yeah, it might not be a very good web server.
Cool. So yeah,
Awesome.
that's basically that. That's everything from my side.
All right. I'll pop
I
it.
hope that was enjoyable.
No, that was great. Like I think, you know, going over all the primitives and then seeing how they're actually implemented under the hood is, you know, like it's not wildly complicated, even though it can feel like it. And I think you did a very great job of just breaking it down and showing us the primitives that we have to work with. And it really, for me personally, just cemented a lot of those things that I had big question marks on. And I'm like, like those now make a lot more sense to me. So to me, that was a really valuable demo. I thought that was great. And I know how the executors work. It used to be something I would shy away from. It's like this function that has a pull on it and stuff like that. So very, very useful. Thank you.
Awesome. Thanks.
All right. Well, we are approaching time. We got a lovely comment there from Russell saying that was an awesome demo. Thank you very much, Senyo and David. I mean, I'll take some of the credit for sure, but it was definitely 100% all Senyo there. So thank you for taking time out of your day, for joining us, and for doing live coding, which I know is no easy feat. So
no, not at all. It's actually my first time, so it wasn't too bad.
Oh, damn it. Oh, well, you did great. Thank you very much.
Thank you.
All right. Well, I'll let you get back to your day. Any final words before we say goodbye?
Cool. I'm good. That was awesome.
All right. Awesome. I'll speak to you again soon. Have a wonderful day. Thank you all for watching. Bye.
Cheers.
Thank you for watching Rawkode Live.